Welcome to our talk on DY-Star, a modular symbolic verification framework for executable cryptographic protocol code. This is joint work with Bhargavan, Abhishek, Bichhawat, Quoc, Pedram, Hosseyni, Ralf, Küsters, Guido, Schmitz, and Tim Würtele. This talk will be given by Abhishek.
Hello everyone.
And me, Guido. We are in a golden era of cryptographic protocols. These protocols are everywhere, be it HTTPS, which is almost ubiquitous. We have secure messaging protocols like Signal, various single sign-on protocols, protocols to secure wireless connections, and protocols to perform payments, for example. The community is also preparing for the age of powerful quantum computers and also taking care of constrained devices. And as we know from the news, it's very hard to get the security of such protocols right. One of these protocols is the Signal messaging protocol. At its core, Signal contains an asynchronous continuous key exchange, which is based on Diffie-Hellman. To recall, if two parties, say Alice and Bob, use Diffie-Hellman to negotiate a shared secret, they do the following. Alice chooses a random value x and sends g to the x to Bob. Bob in turn chooses a random value y and sends g to the y to Alice. Now both parties can compute g to the xy and use that value as a shared secret. Signal, however, is much more complicated than that. It is based on multiple sub-protocols like the X3DH protocol, which is used for the initial key exchange. We have the DH ratchet mechanism, which is used to continuously negotiate new session keys to provide post-compromise security. We have the hash ratchet mechanism to provide forward secrecy, and the actual messages are exchanged with authenticated encryption. And this whole protocol is inherently recursive. So the security of each message depends on a chain of derived keys. And the question is, can we mechanically verify that this protocol is secure? So far, there have been only two mechanized analyses on Signal, and they are based on ProVerif and CryptoVerif. And these analyses only take a very abstract model of the Signal protocol into account. So they only model the X3DH and the double ratchet subprotocols, and these in a quite abstract way. And further, to tame the verification burden, they heavily restrict the overall analysis to only 3 message rounds. So these analyses do not account for the inherent recursion and the unbounded loops that Signal is based on. So can we do better? And if we look at the landscape of verification tools for security protocols, we have two directions. On the one hand, we have computational tools like CryptoVerif and EasyCrypt, which yield quite strong guarantees as you reason on actual bit strings and perform probabilistic reasoning. However, the verification burden in these tools is very high, so you typically are only able to focus on the cryptographic core of a protocol. On the other hand, we have symbolic tools like ProVerif, Tamarin, or RCF. And these tools tame this complexity of the verification by having an abstract view on cryptography and also on messages. So these tools are better suitable to analyze very complex protocols like Signal. In symbolic approaches, we have two lines of work. We have device-style tools like Tamarin and ProVerif, which focus mainly on the protocol core and aim at automation. In these tools, you reason on a global trace and state your security goals on that trace. And you also have equational theories at hand. However, these tools also have their limitations. You typically reason on quite abstract models. You have only bounded data structures, no modularity, and limited inductive reasoning. And it's hard to get your models interoperable with real-world counterparts. On the other hand, we have work based on dependent types like RCF and F7. And these focus on implementation aspects. You have quite modular proofs, you reason on actual implementations, you have unbounded data structures available, you can perform inductive reasoning, your models are automatically executable, and you can create models that are even interoperable with real-world counterparts. But also here we have some limitations. We do not have a global trace, so we are missing a global view. And this limits our expressivity with regard to our security goals. We also only have limited support for mutable state. In general, we have less automation, and we do not have equational theories. With DY-Star, we bridge the gap and aim to combine the best of both worlds. Our approach is based on the F-star programming language. And now, Abhishek will take over and explain more.
F-star is a functional programming language that is aimed at providing guarantees and proving properties about the code. Previously, F-star has been used for computational protocol analysis, but hasn't been used for symbolic analysis. Its powerful dependent type system and the proof environment allows us to easily model and verify unbounded and recursive protocols with complex data structures. The DY-star framework assists in modeling systems that have peers communicating and exchanging messages with each other using different protocols. The communication happens over an untrusted network that is controlled by a Dolev-Yao adversary, meaning the adversary can intercept and modify messages but cannot read encrypted messages without using the corresponding decryption key. We also allow dynamic compromise of principles by the adversary. So one of the main components of DY star is the global execution trace that records the history of states of all principles and the communications at all times throughout the execution. So an adversary can see all the messages that are recorded on the trace and the states of compromised principles. The lowest layer of the symbolic runtime model defines crypto primitives and encodes the Diffie-Hellman equational theory. A protocol is written as a set of functions, each of which defines one protocol step performed by a principal. Parameters to these functions allow the adversary to specify which session of the protocol is to be invoked and which message a principal is supposed to read from the network. We prove security properties for the trace by using an abstract labeling layer that reasons about the secrets used in the protocol. We refine the types of each function on their symbolic runtime layer to help preserve labeling constraints and invariants. The protocol code that uses this labeling layer and type checks is guaranteed to not reveal secrets to the adversary. These invariants allow us to prove generic security properties for the model once and for all. As an application of the DY-star framework, we modeled and verified the signal messaging protocol. The signal protocol uses multiple Diffie-Hellman operations to provide strong security guarantees against adversaries who can compromise both short-term and long-term secrets. As mentioned earlier, while signal has been analyzed with mechanized provers, these analyses had to restrict the protocol for providing the guarantees. Ours is the first mechanized proof of forward secrecy and post-compromise security of the protocol that involves unbounded number of protocol rounds. It is also the first dependent type-based system to model and verify the security features of this protocol. In addition to this protocol, we modeled various classic protocols like the Needham-Schroeder protocol and the ISO variant of the Diffie-Hellman key exchange. To summarize, in this golden era of cryptographic protocols, DY-star is a verification framework for reasoning about the security properties of these protocols. It overcomes the limitations of previously existing verification tools by allowing us to model low-level implementation features of protocols and to precisely reason about the global execution trace. We can also derive interoperable reference implementations from the verified protocol models. However, we only verify trace-based properties and do not support equivalence-based security goals for confidentiality and privacy yet. We plan to improve on these limitations in future and would like to apply DY-star to the verification of the more complex web infrastructure model. Thank you.